Section 3.6, Zeros of Polynomial Functions. Polynomial division is a very useful tool for helping us find zeros of polynomials. To start our investigation, we're going to talk about the following theorem, which we refer to as the division algorithm. The division algorithm states, let P of x and D of x be polynomials, then there exist polynomials Q of x and R of x, where R of x has a degree less than D of x, such that P of x equals D of x times Q of x plus R of x. The Q of x and the R of x is what we would obtain from doing the polynomial division when we divide P of x by D of x. What the division algorithm tells us is that when we do this division, we're finding this Q of x and R of x that satisfies this theorem. We're going to spend a lot of time focusing on dividing by x minus c. When we divide it by x minus c by the division algorithm, our remainder is always going to be constant. So when we divide P of x by x minus c, that's going to allow us to write P of x as x minus c times Q of x plus R, where Q of x would be the quotient from the polynomial division, and R would be the remainder. Thanks to this ability to rewrite our P of x as x minus c times Q of x plus R, this leads us to what we call the remainder theorem. The remainder theorem states if P of x is a polynomial, then P of c is the remainder of P of x divided by x minus c. The reason why this is true, if we plug c into our polynomial form, x minus c times Q of x plus R, we get that P of c equals c minus c times Q of c plus R. Even though we don't know what Q of x is, meaning we don't know what Q of c will be, it doesn't matter. Because if we look at c minus c, we know that will be 0, and anything times 0 is 0. So the product of c minus c times Q of c winds up being 0, and 0 plus R is R. Now there's two different uses for the remainder theorem. If we take a look at example 1, we want to find the remainder of x to the fourth minus 5x minus 11 when it is divided by x plus 2. Now we could go through the division and find the remainder that way. But as an alternative, if we name f of x x to the fourth minus 5x minus 11, we can apply the remainder theorem to figure out the remainder, because x plus 2 is the same as saying x minus negative 2, which means our c in our remainder theorem that we would use is negative 2. So our remainder of our polynomial division would be f of negative 2, and when we plug negative 2 into our function, f of x, we get 15. The remainder we would obtain through the polynomial division would be 15. Now we're going to use the remainder theorem to evaluate P of 3 when P of x equals x to the fifth minus 4x to the fourth plus 3x cubed minus 2x plus 1. Now we could just plug 3 into our polynomial function and evaluate it as we've done before, but it does have its drawbacks. For example, we do have to deal with some very large powers, and we do have a lot of terms in our polynomial. So we could wind up multiplying and adding with really large numbers very quickly. Since we're trying to evaluate P of 3, our c from our remainder theorem will be 3. So to figure out what P of 3 will be, we can perform the polynomial division of x to the fifth minus 4x to the fourth plus 3x cubed minus 2x plus 1 divided by x minus 3. Now we could use long division, but here's where synthetic division shines. We know our c is 3, and we'll list our coefficients. And what's great about the synthetic division is evaluating our polynomial is reduced to a series of addition and multiplication, and we don't have to worry about running into very, very large powers. So now that I have the synthetic division set up, let's go ahead and perform it. Bring down the leading coefficient. Now the series of multiplication and addition. 3 times 1 is 3. Negative 4 plus 3 is negative 1. Negative 1 times 3 is negative 3. 3 plus negative 3 is 0. 0 times 3 is 0. 0 plus 0 is 0. 0 times 3 is 0. Negative 2 plus 0 is negative 2. Negative 2 times 3 is negative 6. 1 plus negative 6 is negative 5. Since we're just trying to evaluate P of 3, all that matters is our remainder. Since our remainder is negative 5, that means P of 3 equals negative 5. Now we're going to look at a helpful theorem that's going to help us factor polynomials that we couldn't factor before through traditional methods. And this theorem is referred to as the factor theorem. The factor theorem states, let P of x be a polynomial. C is a 0 of P of x if and only if x minus c is a factor of P of x. This comes from a direct result of our remainder theorem. In order for x minus c to be a factor of P of x, that means x minus c has to divide P of x, which means when we do P of x divided by x minus c, we get a remainder of 0. And if we get a remainder of 0, that means P of c has to equal 0, which means c is a 0. So if we take a look at example 2, we're going to let P of x equals 2x cubed minus 3x minus 10. We're going to start first by showing that x minus 2 is a factor of P of x. Now there's a couple ways we can do this. The big thing is we want to show that P of 2 equals 0. This is because in order for x minus 2 to be a factor of P of x, that means c equals 2 would have to be a 0 of our polynomial, meaning if I take 2, plug it in to our polynomial, it should give me 0. Now I could go ahead and just take 2 and plug it in, but I'm going to use the synthetic division to evaluate my polynomial at x equals 2. And this is going to serve two purposes that I'm going to discuss later. First, set up our synthetic division. C is 2, and our coefficients are 2, 0, negative 3, and negative 10. Now that our synthetic division is set up, let's perform it. First, bring down the 2. 2 times 2 is 4. 0 plus 4 is 4. 2 times 4 is 8, 8 plus negative 3 is 5, and 2 times 5 is 10, negative 10 plus 10 is 0. Since our remainder is 0, that tells us that p of 2 does equal 0, which by the remainder theorem tells us that x minus 2 is a factor of p of x. Now this work is also going to help us in the next bullet point. We want to find all zeros of p of x, which means we're trying to solve the equation p of x equals 0, which means we're trying to solve 2x cubed minus 3x minus 10 equals 0. Now, if I didn't do the first bullet point, I would be stuck here because I don't know how to factor this polynomial. But I do know that x minus 2 is a factor thanks to our work in the previous bullet point. But x minus 2 times what is equal to 2x cubed minus 3x minus 10? Well, the answer of what will go into these parentheses comes from our work with the synthetic division. From our synthetic division, p of x divided by x minus 2 is equal to 2x squared plus 4x plus 5. So thanks to the division algorithm, that's what goes in place in these parentheses. Now from here, we've factored our cubic polynomial down to a linear polynomial and a quadratic polynomial. Now, if you can factor the 2x squared plus 4x plus 5 quickly, go ahead and factor it. As long as our factors are linear and quadratic, we have enough of our polynomial factored in order to solve. If we set each of our factors equal to 0, first we have x minus 2 equals 0, and 2x squared plus 4x plus 5 equals 0, and 2x squared plus 4x plus 5 equals 0. If x minus 2 equals 0, this gives us x equals 2 as one of the zeros. Now, as for the 2x squared plus 4x plus 5, we can solve that using quadratic formula, which recall quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. 2 would be a, 4 would be b, and 5 would be c. So we plug in our values, and then we can simplify. Now, when we do a little bit of simplifying, we have negative 4 plus or minus the square root of negative 24 over 4. Since we're taking the square root of a negative number, that means our answer is going to be imaginary, so we want to put the I representing the square root of a negative number. And if we simplify root 24, we get 2 root 6, which now if we reduce everything down a little bit more, we get negative 1 plus or minus I root 6 over 2. So my other two roots would be negative 1 plus I root 6 over 2 and negative 1 minus I root 6 over 2. So altogether, I do have 3 zeros, one that's real, the other 2 that are imaginary. If you recall from 2 sections ago, a degree 3 polynomial will have 3 complex zeros when we account for multiplicity. Since we have 3 complex zeros, we did successfully find all of our zeros to our polynomial. Now we're going to find all zeros of p of x, which equals x to the 4th plus x cubed minus 5x squared plus x minus 6, given that x equals negative 3 is a zero of p of x. Since we're trying to find the zeros, that means we're trying to solve the equation p of x equals 0. Now, since p of x is a polynomial, we need to try to factor x to the 4th plus x cubed minus 5x squared plus x minus 6. And unfortunately, looking at it, I'm not quite too sure how to do this through grouping or any other special rules we know. But they did give us a hint that we can use to help us start factoring. They told us x minus 3 is a zero of our polynomial. That means that x minus negative 3, which is equal to x plus 3, is a factor of our polynomial p of x. So p of x can be written as x plus 3 times some other polynomial. The problem is, what is this other polynomial? To figure out what the other polynomial is, we'll perform synthetic division, where we divide our p of x by x plus 3. In our synthetic division, our c would be negative 3. Now we'll list the coefficients of p of x. Now we perform our synthetic division, bring down, multiply, add, multiply, add, multiply, add, multiply, add, and we get 0 as our remainder, which is what we were expecting to get. So through the polynomial division, p of x divided by x plus 3 is equal to x cubed minus 2x squared plus x minus 2. So that would be the factor that would go in our parentheses here. Now, thanks to the 0, we were able to factor our p of x a little bit. But since our other factor is still cubic, we do want to try to see if we can factor farther into linear and quadratic factors. Fortunately for us, the x cubed minus 2x squared plus x minus 2 can be factored by grouping. We'll group the first 2 terms and the last 2 terms together. In the first 2 terms, I'll factor out the x squared. In the second 2 terms, I'll factor out 1 since there's no common factor. And now we notice inside of our brackets, x minus 2 is a common factor in the 2 terms. So we can factor out x minus 2, and we get that x cubed minus 2x squared plus x minus 2 factors to x minus 2 times x squared plus 1. Since we factored the x cubed minus 2x squared plus x minus 2, I can drop these square brackets, and I've successfully factored my polynomial to linear and quadratic factors. And x squared plus 1, I can't factor any farther. So we'll set each of our 3 factors equal to 0 using our zero factor principle, and we'll solve each resulting equation. With x plus 3 equals 0, that means x equals negative 3, which was the 0 that we were already given. X minus 2 equals 0 means that x would have to equal 2. As for the x squared plus 1, we would subtract over 1. So x squared equals negative 1. Square root both sides. Now remember, when we square root both sides, don't forget to plus or minus. And the square root of negative 1 is I. So here we have 4 zeros, negative 3, which we were given, 2, and plus or minus I, which we just found. All of these zeros have a multiplicity of 1. P of x was a 4th degree polynomial, and we did get 4 zeros. Now, here, in order for us to do this problem, we had to know that x equals negative 3 was a 0. The question that you should all have now is, what happens if I don't know either one of the factors or the 0 of the polynomial we're trying to find the zeros of. We're going to attempt to answer that question with the next theorem. The next theorem is going to help us limit down the possible values of zeros of polynomials. This theorem is referred to as the rational zero theorem. In order for the rational zero theorem to work, p of x needs to be a polynomial with integer coefficients. And we're going to let the leading coefficient be an and the constant term be a sub 0. If the number p over q, where p and q are integers that have no common factors other than 1, is a 0 of p of x, then p has to be a factor of a sub 0, our constant term, and q has to be a factor of a sub n, our leading coefficient. What this theorem allows us to do is it allows us to narrow down possible candidates of a rational zero for our polynomial. So if we take a look at p of x, which is x cubed plus 4x squared plus x minus 26, we do want to find all the zeros of this polynomial. However, they don't tell us any zeros to start off with or any factors like we saw in the past two examples. So we need to figure out a zero for ourselves. Thanks to the rational zero theorem, I now have an idea of what my rational zero should look like. They should be in the form of some factor of my constant term, which is 26, divided by some factor of my leading coefficient, which is 1. To figure out what all my possible rational zeros are, we're going to start listing our factors of 26. And we're going to ignore the sign, although that does play a role later. Now we know 1 is a factor of every number, and 1 times 26 gives us 26. 2 divides 26. 26 divided by 2 is 13. And that looks like that would be all the factors of 26. Now, keep in mind, our factors could be positive or negative, because I could multiply negative 1 and positive 26 to get negative 26. So to account for the positive and negative factors that can multiply together to give me negative 26, I'm just going to throw in a plus or minus. Even if my constant term was positive, I would still put plus or minuses, because I can multiply two negatives to get a positive. Now I'm going to list all my factors of the leading coefficient, which is 1. 1 only has one factor, which is itself. And just like with the factors of 26, I'm going to put plus or minus to account for the fact that I could multiply two negatives together to get positive 1. From here, we can now begin to list our possible rational zeros, which I'm going to abbreviate PRZ. The way we're going to obtain our possible rational zeros is we're going to take each factor of 26, which is our constant, and we're going to divide it by each factor of our leading coefficient, which is 1. 1 divided by 1 is 1, 2 divided by 1 is 2, 13 divided by 1 is 13, and 26 divided by 1 is 26. And we are going to include the plus or minus, as we could divide with either positive 1 or negative 1 with any combinations of the plus or minus factors above. So my possible rational zeros for my polynomial equation are 1, negative 1, 2, negative 2, 13, negative 13, 26, and negative 26. Now, not every number in this list is going to be a possible rational zero. But if my polynomial does have a rational zero, it has to come from this list. Now we have to perform trial and error to figure out which of these 8 candidates are actually a zero to our polynomial. And here, we're going to use synthetic division, because using synthetic division will not only allow us to check to see which of our 8 numbers is a zero, but also give us the factor that we would need to help us continue to factor the polynomial. First, we'll guess 1, and we'll set up our synthetic division with our coefficients from p of x. Now we perform the synthetic division, and at the end of the synthetic division, we get negative 20. Unfortunately, that tells us 1 cannot be a zero, because if I take 1, plug in my polynomial, I'd get negative 20, so we'll cross positive 1 off the list. From there, we'll guess our next possible rational zero. Now I will try negative 1. So you see I cleaned up my synthetic division from when I tried 1, and I'm just going to the next number on the list. Now it doesn't matter what number you guess next, but you do want to try to be systematic and organized with your guesses. Go through the synthetic division like we did before, and when we perform the synthetic division with negative 1, we see the remainder is negative 24, which tells us negative 1 is not a zero, so we'll cross that off from the list. Now we'll try the next number on the list, which is 2. Now I have the synthetic division set up for 2, and we're going to perform the synthetic division once again. And when we perform our synthetic division with 2, we see that we have a remainder of 0, which is precisely what we want to see. Now what this tells us is 2 is a zero of our polynomial, which means x minus 2 is a factor of our polynomial. The other factor we would multiply with x minus 2 to get p of x is the quotient of our synthetic division, which is x squared plus 6x plus 13. Since we're trying to find the zeros, that means we're setting our polynomial equal to 0. And since we have our polynomial now factored into linear and quadratic factors, and it doesn't appear that x squared plus 6x plus 13 factors any farther, we can go ahead and use the zero factor principle, and we can set each factor equal to 0. When we solve the first equation, we get x equals 2, which is what we expected from the synthetic division. For the next equation, the x squared plus 6x plus 13 equals 0. Since we can't factor it, we'll go ahead and use the quadratic formula. And after using quadratic formula, we get that x equals negative 3 plus or minus 2i. So our 3 zeros are x equals 2, which we got from the synthetic division, and the imaginary zero is negative 3 plus or minus 2i. Now, while this process of guessing zeros can be rather tedious, try to make sure you're staying organized with your guesses, and keep in mind that it is very possible that you would have to exhaust the entire list just to find one rational zero. It's also possible the polynomial doesn't have any rational zeros to begin with, which unfortunately can only be seen once when you have exhausted the entire list. If the polynomial doesn't have any rational zeros, that's when we would turn to numerics methods where we would try to approximate the zeros using the intermediate value theorem or other techniques that were developed to help us find irrational zeros or even imaginary zeros. Now we're going to find all the rational zeros of 4x to the fourth plus 20x cubed plus 29x squared minus 49x plus 13. Just like in the last example, they didn't give us any zeros, nor did they give us any factors of p of x. So to help us try to factor it, we'll turn to the rational zero theorem and start listing our possible rational zeros. Our constant is 13, so we'll start by listing the factors of 13, which is plus or minus 1 and plus or minus 13. Our leading coefficient is 4, so we'll list our factors of 4, which are plus or minus 1, plus or minus 2, and plus or minus 4. Now we can list our possible rational zeros. We'll start by dividing our factors of 13 by 1. 1 divided by 1 is 1. 13 divided by 1 is 13. So 4 of our possible rational zeros are plus or minus 1, plus or minus 13. Now we'll divide our factors of 13 by 2, and we get plus or minus 1/2 and plus or minus 13 over 2. Then we'll divide our factors of 13 by 4, and we get plus or minus 1/4 and plus or minus 13/4. Now we'll start guessing zeros and perform the synthetic division. We'll start by listing the coefficients of our p of x, and now we'll start guessing at zeros. First, we'll guess 1, and then perform the synthetic division. And after performing the synthetic division, we see that the remainder would be 20, which means 1 is not a rational zero. So we'll move to our next guess of -1. And when we perform the synthetic division, we get that the remainder is 72, which means -1 is not a zero either. So now we'll move on to 13. And after performing the synthetic division with 13, we see that 162,500 is the remainder, which means 13 can't be a zero. So now we'll try -13. And after performing the synthetic division with -13, we get a remainder of 75,816. So -13 will also not be a zero. So now we'll move on to the next number on the list, 1/2. And when we perform the synthetic division with 1/2, we get a remainder of 0. Now we know a little bit of how to factor our p of x. One factor is x minus 1/2, and our other factor is 4x cubed plus 22x squared plus 40x minus 26. Now the problem becomes, how do we factor the 4x cubed plus 22x squared plus 40x minus 26? Remember, we want our factors to be either linear or quadratic, because those are the two easiest polynomial equations to solve. But looking first at the 44x cubed plus 22x squared plus 40x minus 26, I do see all the coefficients are even. So we can factor 2 out of our second factor, and we'll move the 2 to the front. Now, unfortunately, I can't factor it any farther via grouping. So what we have to do instead is we would have to apply the zero factor principle to the 2x cubed plus 11x squared plus 20x minus 13 to try to find a zero of our second factor and then be able to factor it farther. So let's go ahead and start with that approach. Now, focusing solely on the 2x cubed plus 11x squared plus 20x minus 13, we can see that the constant term is 13, which we already know the factors are plus or minus 1 and plus or minus 13. The leading coefficient is 2, which give us plus or minus 1 and plus or minus 2 as factors. So our possible rational zeros for our second factor would come from dividing our factors of 13 by our factors of 2, just like what we did before. And we have plus or minus 1, plus or minus 13, plus or minus 1/2, and plus or minus 13 over 2, which is a slightly smaller list than what we had before. Now, it might seem as if, okay, I still have 8 zeros I have to check. I have to go through this long process again. However, we can use our past failures to help us here. We already determined when we were trying to factor our original p of x that 1, -1, 13, and -13 could not be zeros of p of x. Well, if they're not zeros of p of x, they cannot be zeros of the 2x cubed plus 11x squared plus 20x minus 13. So there's no point in us checking them again. Now, even though 1/2 was a zero of p of x, it can still be a zero of our second factor, because remember, zeros can repeat. So we'll set up our synthetic division, and we'll start off with our guess of 1/2, which we knew was a zero before, but now we're just checking to see if it can be a zero again. And we see through the synthetic division, we get a remainder of 0. So 1/2 is a zero, the 2x cubed plus 11x squared plus 20x minus 13. Now our other factor comes from our quotient in our synthetic division, which is the 2x squared plus 12x plus 26. Now I have my polynomial factored into a product of linear and quadratic factors, which is precisely where we want to be, because from there we can either solve our linear factors or use quadratic formula if we need to. But let's still see if we can factor the 2x squared plus 12x plus 26 any farther, because we do see that 2 is a common factor, and 2 times 2 is 4, and the x minus 1/2, since they repeat, we'll simplify that to x minus 1/2 squared, and when we factor out a 2 from the 2x squared plus 12x plus 26, we get x squared plus 6x plus 13. Unfortunately, we can't factor that any farther, but that's perfectly fine. Since we're setting this function equal to 0 to find its roots, all I need is my linears to be linear or quadratic. So now we'll set each factor equal to 0. When we solve our first resulting equation, dividing by 4, taking the square root and adding over 1/2, we get x equals 1/2. And our second equation, we have to use the quadratic formula. And when we solve our second equation, we get -3 plus or minus 2i. So our zeros to our polynomial is 1/2, which will have a multiplicity of 2 because of the x minus 1/2 squared, and the -3 plus or minus 2i. When we account for multiplicity, we do have a total of 4 zeros, which makes sense because we did solve a 4th degree polynomial. So keep in mind, sometimes you may have to use the rational zero theorem more than once, especially if you're working with a degree 4 or higher polynomial. But make sure you do keep track of what zeros did not work, because if they didn't work before, they're not going to work later. So it can help narrow down your guesses for when you're trying to factor that next polynomial. Now, something we may have noticed in our past few examples is every time that we got imaginary zeros, they always came in pairs. Turns out this was not a coincidence. Our next theorem that we're going to take a look at tells us that this is true in general. And this is referred to as the complex conjugate theorem. If p of x is a polynomial with real coefficients with a complex zero of the form a plus bi, then a minus bi is also a zero of our polynomial p of x. So this theorem tells us that complex zeros always come in pairs, and those pairs are going to be conjugates of each other. One of the things we discussed in a previous section was that a polynomial of degree n has n zeros when we account for multiplicity. The reason why this is true is due to the fundamental theorem of algebra. The fundamental theorem of algebra states if p of x is a polynomial of degree n greater than or equal to 1, then p of x has at least one complex zero. In combination with the factor theorem, these two tell us that any polynomial can be factored into exactly n, not necessarily distinct, linear factors. And the reason why the factors may not necessarily be distinct is because of the multiplicity of our zeros. Another way to phrase this is any polynomial of degree n greater than or equal to 1 can be written as p of x equals a times x minus r1 times x minus r2, all the way down to x minus rn, where the ri's represent the roots of our polynomial, which again are not necessarily distinct, and a is the leading coefficient of the polynomial. This form is referred to as the factor form, and we discussed this in a previous section. Now for our next example, we're going to write the equation of a fifth degree polynomial with roots of x equals 1 with multiplicity 2, x equals 0, and x equals 1 plus I. And we're told this polynomial has a leading coefficient of 1. So to write our equation in factor form, we need to identify the leading coefficient and the roots of the polynomial. Now here, they tell us the leading coefficient is 1, so we know that a will be 1. So our p of x is going to equal 1 times a product of x minus our roots. Now, if we look at our roots so far, we're told that 1 has a multiplicity of 2, so x minus 1 is going to be a factor of p of x, but because it has multiplicity 2, this factor will be squared in our factored form. Our next 0 is 0 itself, so x minus 0 is a factor. And lastly, we're told that 1 plus I is a 0, so our next factor is x minus the quantity 1 plus I. Now, the problem we have is right now our p of x is a fourth degree polynomial, but the problem tells us we want a fifth degree polynomial. Well, keep in mind, we were given a complex root. We were told 1 plus I was one of the roots. So thanks to the complex conjugate theorem, the conjugate of 1 plus I, which is 1 minus I, must also be a root. So our next factor will be x minus 1 minus I. And there, we now have a fifth degree polynomial. We can do a little bit of cleaning up. Anything times 1 is itself, so we won't write the leading coefficient of 1 anymore. X minus 0 is x, which will look nicer when we bring it to the front. Then times the x minus 1 squared. And then we'll distribute the negative signs into the two complex roots that we see above to get x minus 1 minus I and x minus 1 plus I. And there's our factored form of p of x. The next part, they want us to find the standard form. We'll find the standard form by expanding out p of x. This can be a little bit tedious, but if you use the special multiplication rules you've learned in the past, this can be a little bit quicker. I'll start by squaring the x minus 1. To square the x minus 1, we'll use the formula that a plus b squared equals a squared plus 2ab plus b squared. So x minus 1 squared is x squared minus 2x plus 1. Note you could also write x minus 1 as x minus 1 times x minus 1 in FOIL, but using the formula is a little quicker. As for the next two factors, the x minus 1 minus I and the x minus 1 plus I, notice that the sign in front of i's are opposites. In order to efficiently multiply those out, we're going to use the difference of squares formula. That is a plus b times a minus b equals a squared minus b squared. And we're going to group within our factors the x minus 1 together. So the x minus 1 would be the a, I would be the b. And if we multiply that out, we get x minus 1 squared minus I squared. Next, we're going to distribute in the x, and in the x minus 1 squared, which we've already expanded out before, which is x squared minus 2x plus 1. And recall that I squared equals negative 1. So minus I squared becomes plus 1, and 1 plus 1 combined to give us plus 2. Now we have to FOIL. Now when we FOIL, we're going to be very careful. We're going to try to organize our product so that way collecting like terms is easier. So if we first multiply in the x cubed term, we get x to the fifth minus 2x to the fourth plus 2x cubed. Then multiply in the negative 2x squared term. Now since negative 2x squared times x squared is negative 2x to the fourth, I'm going to put underneath the negative 2x to the fourth that we found earlier when we were distributing in the x cubed. Then plus 4x cubed and minus 4x squared. Then distribute the x times x squared is x cubed. So I'm going to put that underneath the x cubed terms, then minus 2x squared, then plus 2x. Now I can collect my like terms a lot more effectively because I have all of my powers lined up. X to the fifth, nothing to collect. Negative 2x to the fourth plus negative 2x to the fourth is negative 4x to the fourth. 2x cubed plus 4x cubed plus x cubed is plus 7x cubed. Negative 4x squared plus negative 2x squared is negative 6x squared, and the 2x has nothing to collect with. So our p of x in expanded form, or standard form, is x to the fifth minus 4x to the fourth plus 7x cubed minus 6x squared plus 2x. The last theorem we're going to look at in this lesson is one that can be very useful for telling us what type of numbers we should be focusing on for our guesses when it comes to using the rational zero theorem. Now, this theorem is called Descartes' rule of signs. It is named after a French mathematician, so I'm probably mispronouncing the name. So the rule states, let p of x be a polynomial with real coefficients. The number of positive real zeros is equal to the number of sign changes of f of x or less than the number of sign changes by an even integer. Before we move to the next part of the rule, let's take a look at what that means. If I want to try to predict how many positive zeros my polynomial f of x has, what I would do is I would look at the changes in the signs. If we look carefully, from negative x to the fifth, from negative 4x to the fourth, there's no sign change. Same thing goes if we go from negative x to the fourth to negative 3x cubed, no sign change. But if we go from negative 3x cubed to 6x squared, we went from subtraction to addition, so there's a sign change. And then going from the 6x squared to the negative 4x, there we go from plus to minus, we have a sign change. And then from negative 4x to negative 12, no sign change. Because there were two sign changes in our polynomial f of x, that tells me my polynomial can have at most two positive zeros. Now, what about the part where it changes by an even integer? 2 is the most zeros I can have. Well, if I don't have two zeros, because of this change by an even integer, it's impossible for my function to have one positive zero. So from there, it turns out when I do 2 minus 2, I get 0. That means I have either two positive zeros or zero positive zeros. It would be impossible for me to have only one positive zero for this particular polynomial. The second part of the rule helps us determine the number of negative zeros. The number of negative real zeros is equal to the number of sign changes of f of negative x, or less than the number of sign changes by an even integer. So to try to figure out the number of negative zeros, we'll find f of negative x, which means everywhere we see x in our original polynomial, we'll replace with negative x. Negative x to an odd power would be negative x to that odd power, while negative x to an even power would just be x to that power. So anywhere where I have an odd power, my sign is going to change, while my even powers, my sign is going to remain the same, which means f of negative x equals x to the fifth minus 4x to the fourth plus 3x cubed plus 6x squared plus 4x minus 12. Now I'm going to count the number of sign changes because that'll help me determine the number of negative zeros. Well, starting off from x to the fifth to negative 4x to the fourth, there's a sign change. The negative 4x to the fourth to the positive 3x cubed, there's a sign change. And our signs stay positive all the way to the 4x, which changes signs to negative 12. So here, we see that there has to be at most 3 negative zeros. Now, because of the differ by an even integer, because 3 is the maximum of the number of negative zeros I can have, that means I can't have two negative zeros. So the next possibility would be 3 minus 2, which is 1. And from there, to find the next possibility, I would subtract 2 again. But if I subtract 2 from negative 1, I get negative 1, which I can't have negative 1 of something. So my polynomial can either have 2 positive zeros or no positive zeros, or it can have 3 negative zeros and 1 negative zero. What's great about knowing this is I'm guaranteed to have a negative 0. But the 0 may not be rational. But at the very least, since I know I have to have a negative 0, that would tell me it would be worth my time to guess and check the negative possible rational zeros first when applying the rational zero theorem.